All right, welcome to this video. We're going to talk today about center of mass and then linear momentum. So when we're talking about the center of mass of a system of particles is the point that moves as though all of the system's mass were concentrated at one point. So up to this point, we've talked about point masses, but now we're going to talk about masses that act as one mass. So if I have a series of masses, wherever they are, they're going to act as if they have one mass controlling them. And so Newton's laws are going to apply for these centers of mass. It's going to act on the center of mass, even if it doesn't exist on a specific object, it exists in space. So there's a formula for the center of mass. Center of mass formula is for the x component is x center of mass is mass 1 times position 1 plus mass 2 times position 2 over mass 1 plus mass 2. And we're going to learn later that that's going to extend also for multiple masses. So there's two different ways you can do this center of mass. You can define your axis away from the masses, or you can define your axis on one of the masses. So one of the best ways to do this is to always define an axis on top of one of your masses, because what you're going to do is your position of that first mass is going to become 0, and you're going to eliminate that mass from the equation. So it's very convenient to try to do this. So this is where the concept of symmetry comes into play. It's very important. So if we look here, you can see like I said, on the left-hand side that this is from the origin. The origin is on mass 1. But if the origin is not on mass 1, then you have to include that new distance from the origin to mass 1 and then the distance to mass 2. Now notice that the center of mass is going to be in between these two masses. So if mass 1, let's say in this situation, is much smaller than mass 2, if mass 2 is greater, that center of mass is going to be closer to the bigger mass. If they're equal, it's going to be right in the middle. Notice that center of mass doesn't change even if I start my origin over here. It's still between these two masses and closer to the bigger mass in this case. Now, before we talked about in physics how sometimes they overuse letters over and over again to mean different things. So one of the things you're going to see is the letter R for radius. So radius can actually be the radius of a circle, or it can actually be the distance between two centers of mass. In this specific example, we use the letter D to show that distance between the two centers of mass, but just note this notation here that when we get to gravity, that's going to be R, the distance between the two centers of mass. It's not necessarily a radius in terms of a circle, but that's just something that they use. Also notice that we use x1 for the distance from the origin to mass 1 and x2 from the origin to center of mass 2. X center of mass, XCOM is the position to the center of mass. We use lowercase m's here, little m's with subscripts, lowercase x's here, and we use the capital letter M to denote that we're talking about the total mass. Sometimes I will use like a little t there just to show total mass, just to clarify that. But the terminology really becomes important to understand, because as we get into these nuances, it becomes rather challenging to keep up with all of this if you're not clear about that. Now, the center of mass takes place in 3 dimensions, so we calculate each one separately. So if we take this center of mass equation here, first of all, and we take out the mass total here, this big M, we take it out, we can do a summation notation here, which is the sum of mi xi from I equals 1 to I equals n. And in essence, you're just adding these up. We're going to see later that this becomes an integral, and we integrate these solid bodies across a rigid body of uniform or varying geometry depending on the situation. But this occurs in all 3 dimensions, so you just calculate them and you'll find the x center of mass, the y center of mass, and the z center of mass. So when we talk about solid bodies, in essence, we're just going to take the integral 1 over the total mass times the integral of x dm as mass varies. And this is true for the x, y, and the z. And we're also going to be able to relate this to volumes because we know that there's a relationship between volume. If we look at the equation here, which is rho is mass over volume. And so in essence, the mass is going to equal rho v. So if I take dm equals rho dv, and so rho is the density and dv is the differential. So when we plug that into this equation here, we get rho dv here, and we know that mass, the total mass, is going to be rho times the total volume, that those rho's are going to cancel out. And in essence, you're going to get 1 over v equals the integral of x dv, 1 over v integral of y dv, 1 over v integral of z dv. And you'll also be able to do this with areas too. If the area, like you'll be able to look at areas and find centers of mass because you'll be able to take it as a function of the area if you have a uniform thickness, let's just say. So it keeps reducing down, like it reduces to volume and then it reduces to area. So it's a very big play on symmetry in this chapter. Newton's second law, in essence, what we're saying here is that these series of particles um, behave the same as if we had a single particle. It's just that they behave at the center of mass. So like if you have an object going up in the air, and then let's say that you have like a projectile here, and then that projectile explodes into a bunch of different pieces, and those pieces are still traveling through the air, and you have your center of mass, which is really imaginary. I'm just drawing it here. We'll draw it in a different color just so you can see it. So center of mass is pink, it's imaginary. That center of mass keeps following on the same trajectory as a projectile. So all of these laws are valid for the center of mass, and everything we've seen up to this point, we've assumed that there's one point mass at the center of mass, but now it can change depending upon the system. If you have a series of particles, we look at that center of mass as behaving as a single particle. Now we talk about the concept of linear momentum. Linear momentum is a vector, and linear momentum is the letter P. The letter P comes from the term progress. They used to take horse carriages and see how far the horse carriage could keep going after the horse had stopped pulling it. In other words, how much momentum would it have on its own to keep going? So that's where that came from. It's mass times velocity. So what gives the momentum its direction? The velocity does, not the mass, right? Mass is a scalar, velocity is a vector, and the units are kilogram meters per second. And we can relate this to force. The force net is dp dt, the change in momentum with respect to time. And if we differentiate this out, ddt, momentum is mass times velocity. Mass is constant, that comes out. And then we have mass times dv dt, or force equals ma. So in essence, dp dt equals ma. So that's just a quick derivation of that. System of particles. If you have the sum of momentums, it equals the net momentum. So it's very similar to forces. If you have the sum of the forces equals F net, that occurs in the X, that occurs in the Y. And just like forces, you might have a zero net momentum in the X, but you might have a net momentum in the Y. Okay, so you might have, remember we talked about first law, second law, same concept here. You could have zero here, net here, zero here, or net here. A famous problem that people talk about with zero and zero momentum is the concept of the plate dropping on the floor. If you have a plate in the air and it drops down the z-axis and then it hits the floor, right? And it breaks off into these pieces and the pieces go in all these different directions, right? That what happens is your net momentum is zero in the x and the y, and then they go off in different directions when they hit the floor. So that's an example of that. You could have, so it's kind of a strange situation because you're traveling down the z-axis. If you drop a plate, hits the floor and it's going off. And remember, if this adds up to zero, that you have to have one positive y balancing the negative y and a positive x balancing the negative x. So that's important to remember. Momentum may be conserved or not. So uh, again, if you're talking about a two systems, you and the earth and you, of course it's conserved always, but when we talk about conservation, people always say momentum is conserved. And again, of course that's true if you look at both systems, but if we're talking about just our system, If we have a net external force acting, it's not conserved. That's the definition of impulse, which we'll see in a minute. So if you have a change of momentum, you have an impulse. There's an external force acting on that. And when you have collisions just on their own, momentum is typically conserved. Okay. So I want to just say it can be conserved or not because everyone always says momentum is conserved, and that's not always true depending on your vantage point. So again, going down here, um, the definition of conservation means initial equals final. So there was no change. So if we look here, if your initial momentum equals your final momentum, or the change of momentum equals 0, then it's conserved. There's no net external forces acting on the system. Okay, so that's the key with that. Now, collisions and impulse. So let's talk about collisions. So collisions can be with just internal forces if two objects are moving and they collide and then they move off inelastically or elastically. But if there's an external force hitting something like a baseball bat hitting a ball or a ball bouncing off a floor, then you get what's something called an impulse. Impulse is the letter J, it's the change of momentum. Okay. Now this can occur in many different ways. Usually it's just M delta V. Okay, that's usually what it is. However, it can also be delta MV. So can you think of a situation where you're changing your mass? Well, what about if someone's riding on the handlebars of a bike and they jump off that bike? Or what about if there's an airplane traveling and it's dumping fuel out as it goes? Okay, so this one is easier to think of, mass change and velocity. Okay, you hit a ball, the velocity change. Delta mass is a little harder to visualize. And then delta M, delta V. Can you think of a situation where you're changing mass and you're changing velocity? Well, this is the central core of the rocket equation. When you have a rocket moving into outer space, it's losing mass and the speed is also changing. So this becomes a complex differential. You have to apply the chain rule to using calculus to find out that rocket equation. But we're not going to get into that right now. Remember, anytime you see delta, that's a key that you're going to be taking a differential. Delta is a differential. The units of impulse are kilograms meters per second because it's the change of momentum, but sometimes they'll give you a hint and they'll just say Newton seconds. If you hear the term Newton seconds, they're probably talking about impulse. I mean, you could do Newton seconds for momentum, but typically when we say kilogram meter per second, we're talking about momentum. When we say Newton seconds, we're talking about impulse. So that's just the convention. You could use either one in either case. It depends. But I'm just telling you that that's the convention. So let's talk about if you strike an object. So this is a ball being struck here. So here's a bat. Let's say the bat's moving like this. It strikes the ball. So this is my attempt to sketch a baseball. So let's say these are the threads on the baseball here. And there you go. And your bat is striking this. So your wooden bat is striking this ball. And what happens is this bat is going to apply an impulse on this ball. Now, we talked about impulse J being usually M delta V, but it's also F delta T. Now I wrote the term average here, AVG, but the line above it also means average times delta T. So it's a force applied for a period of time. It's also the integral from T1 to T2 of F dt. Remember I told you that there's a hint here. If you see a delta, that's usually a dt. Okay, that's usually what that means. Now, this curve here is a typical curve of an impulse acting on an object. This is the J of, so if you hit a ball, the curve usually looks like this, okay? So if we have anything that's multiplying, the area under that's the area under the curve, right? So we take integral, the area of this is going to be the impulse, okay? So F delta T. All right, so this equation here just finds the average, right? So this is actually the instantaneous. This is typically modeled by sine squared omega t if you're going to model this, but that comes in more in electricity and magnetism. You don't really need to know that. This curve, if you take the average value theorem, the integral of a to b 1 over b minus a of f of x, what you'll get is that the average value here of this force, so F average here, is going to equal 1/2 of the peak. So F peak here is going to equal twice the average force. Okay, that's just it's a curiosity. It looks like, oh, it should be half because it's an average. That's not true. If you took a sine wave, it wouldn't be half. It's a coincidence that it's half, but whatever. I'm just giving you some extra information there. You don't really need to know that. All you need to know is that the average force times the change of time is the impulse. So the total area under this curve behaves as if you took the average force times this time. These are equivalent statements in terms of the areas that you'll get, but they're not quite the same thing. Obviously, you have to integrate sine squared omega t across this if you're modeling it by that function to get it. But just some curiosities here. This is what it really looks like. This is the average force. This is the peak force. It's twice the average force, but it can be accomplished the same way in terms of finding the total area using this, just the average force here to find out that impulse. Same thing. Okay, so if we're talking about a series of particles that the impulse of that is just negative n times delta p. So that's just like if you had like a bunch of little pellets going towards something, the impulse j is negative n delta p. Okay, so it's a very similar concept. It's just applying the n just means there's many particles here, and we said, j equals f delta t, which is the impulse, equals n delta p, and then you can bring that t over, divide that t over to this side, and you get negative m delta v delta t. And then, of course, we know that m delta v over delta t, there you're back to acceleration again there. So all of this kind of ties in together, and it seems like it's repeating itself over and over with these concepts, but it's just important to note. Now, when we talk about velocity change, we need to understand that we have to give it a sign because it's a vector. So if you have a velocity here, let's just say that you have a velocity and you're throwing like a piece of clay onto a wall here, okay? So inelastic, so that's why I'm using the term inelastic, you're throwing it to the wall and then it just sticks to the wall and the V final is 0. So if I take delta V, it's V final minus V initial. So if I'm taking this to be my positive X value like this, I'm going to say that the final is 0 minus the initial V. So my change of delta V is negative V. And that's important when we get to these equations because if it came back the other way, you'd have to account for the change of the velocity, which is this one. If we're talking about an elastic case, a completely perfectly elastic collision in this case, that your initial V initial is V, V final is negative V. So V final minus V initial is delta V. So V final is negative V, and minus V initial, which is positive V, so it's negative 2V. So just something to consider. You will see these situations over and over again. Now let's talk about this. This is an interesting example. There's a ball bouncing here. So here's a ball, and it's bouncing into the ground like this. It comes into the ground and it ricochets and comes back up. And let's just say it comes back with the same exact speed and the same exact, let's say the angles are the same. So what's going on here? Well, this is a collision. Yes. Is momentum conserved? No. Why? How do you know momentum's not conserved? Because the velocity vector changed direction. You see this? The velocity vector changed. So right there, the mass didn't change. If the velocity changed, the momentum changed, period. Okay, so was there a change in the x momentum? Well, let's look at the x. Let's look at the y then the x. Let's do this for the y. Here's the y. Here's the y here. And here's the x here. And these should be symmetrical. I know it's not completely drawn symmetrical, but let's just pretend like they are. So in essence, what happens here is that ball comes down, hits the ground. Now notice this x did not change. The v initial x is the same as the v final x. You see that? So the x, the changed momentum in the x is conserved at 0. No momentum was changed in the x. But there was a big change in the momentum in the y. Why is that the case? It's definitely positive. Okay? because if you're coming down at a negative v and you're going up at a positive v, what is my delta v going to be there? Delta v is going to be v final v minus v initial v, which is going to be 2v. So I changed velocity in the y. And so what's responsible for that? The big J that's coming up here, this is the J, the impulse, is in the y. It caused the momentum to change in the y. J is a vector. J points in the direction of the force. Why? Because J is going to be average force times average time. So what gives J its direction? The force does, not the time. So when something's hitting an object, the J is the impulse that's coming up. And so delta P is 0, delta Py is positive, and the J is going straight up. Now let's talk about inelastic collisions and explosions. This is a case where a momentum is conserved. Okay, I'm not talking about an object hitting a wall or a baseball bat. I'm talking about two objects just coming together. So momentum is going to be conserved. Kinetic energy is not conserved. Why? Because if two objects come together and they hit, let's just say inelastic means they stick. Let's say two objects come and hit like this. There's a situation where two objects can come and hit and their final speed is 0. V final is 0. So you had an initial kinetic energy and you can have nothing at the end. It could all go to heat. That's where it's going. It's going to heat and sound. But momentum is always conserved. And the momentum of the final object is the momentum of the center of mass, always. So that's important. So why is that important? Well, center of mass initial path is the same as the final path after collision. Okay? So initial momentum equals final momentum. And the x and the y, it's conserved. Kinetic energy initial does not equal kinetic energy final. In fact, most of the time that kinetic energy is going to be very low. The ratio of the final to the initial is going to be somewhere usually like really low, like 20%, you only retain 20% of it or 10% of it or super low. Again, it goes to heat or sound. It could go to 0, like we showed in that situation. If two objects hit, they can stop. If two objects stop, obviously kinetic energy is not conserved because you had motion and then there's no motion. Okay, so if you have a situation like this, there's mass 1 moving to mass 2, and they're going to stick, right? Now, this center of mass is already moving. It already has its own path that it's traveling, the velocity of the center of mass. After they hit the center, they're going to become like one mass, and it's going to keep moving off together. So that center of mass it's just continuously moving in the same direction the whole time. Even though they don't touch, that's how the system behaves. So you look at the system like this, and we're just looking at it in the x direction. So we say m1 v initial 1 plus m2 v initial 2 equals m1 plus m2 v final. They move off together. Interesting. Now I'm going to talk about an explosion. So most people think about an explosion. They're like, what's an explosion? I can't think of one. Well, a very simple example is if let's say there's you and there's a boat, right? And you walk off the boat onto a dock. So let's say that here's a boat and here's you and here's the dock, right? So what's going to happen is if you step off this way, the boat's going to go this way. Okay, they're going to go in opposite directions. That's an inelastic explosion. Or dropping a plate on the floor. That's an example. If like it's coming down that z-axis, like I said, and it hits the floor and they go off in different directions, it's an explosion. So in this case, if the two masses are equal, the center of mass is not moving. After it explodes, the center of mass still does not move. It just stays there. Okay. Now it might move if they're already moving and they explode, and the center of mass will keep moving. But if they're stationary, center of mass is going to stay stationary. So it's the reverse of the other one up here. M1 plus M2 V initial times V initial equals negative M1 V final 1 plus M2 V final 2. Notice the signs are important here. When we're talking about momentum, the signs matter. Kinetic energy, the sign doesn't matter. This one, the sign definitely matters. Okay. Also, I also want to point something out here about inelastic collisions. Notice it's very similar to the center of mass equation. Do you remember the center of mass equation? Remember that equation, x center of mass? Okay, So what was X center of mass? M1 X1 plus M2 X2 over total mass, right? Okay. Notice it's almost identical to this to an inelastic collision. You see that? So if I move, so instead of X, we're talking about V. So if I move that over, right, and I said M1 X1 plus M2 X2 equals total mass X center of mass. Look at that. That's like an inelastic collision. The center of mass follows that same kind of logic. So if you ever forget about the center of mass, it's very similar to an inelastic collision, except we're talking about position and not the velocity. Okay, in this example, we're going to talk about the ballistic pendulum example, and this is used to describe the energy of a bullet. In essence, what happens is that you have a bullet that travels, and usually the mass of the bullet is going to be given to you in grams, and you have to turn it into kilograms, so be careful about that. This mass is going to be in kilograms of the block. It's going to strike the block, okay, and then it's going to move it to a certain height. So you're going to use a combination here of momentum and energy, in essence. So uh, you're going to have 1/2 mv squared of this equals 1/2 m1 plus m2 v squared at the impact point B, and then you're going to use 1/2 m1 plus m2 v squared equals m1 plus m2 gh to find out how high it goes. So it's like a chain of events. You're using the kinetic energy, and then your energy initial equals energy final. Okay, so right when it hits, that's the case. Even though this bullet is like tiny, tiny, you still have to put it in. It's in grams. You'll find the speed of this right when it starts moving, and then you'll use that speed using energy to find the height. All right, let's talk about elastic collisions. So when we talk about a perfectly elastic collision, we're not talking about friction, we're not talking about sound, we're not talking about any of that stuff. Momentum is conserved and kinetic energy is conserved. They're both conserved. So P initial equals P final, and kinetic initial equals kinetic final. Now I'm going to give you some one-dimensional scenarios here. I think they're important to memorize. And this is going to start out with mass 1 is moving, mass 2 is at rest. So you have mass 1, mass 2. Notice underneath here, I'm going to put both equations. I'm going to put the momentum equation here, and I'm going to put the kinetic energy equation here. So this is momentum initial, kinetic energy initial, momentum final, kinetic energy final here. Now, first situation, you have mass 1 is less than mass 2. So what happens here? Well, mass 1 is moving, it hits mass 2, and then mass 1 goes back to the left, and mass 2 goes back to the right. So qualitatively, I want you to understand that a little object striking a big object will ricochet back in the opposite direction. Okay, and this is what the momentum and the kinetic energy equations will look like. The initial one is at rest, so there's no momentum, no kinetic energy in the initial. So you just have all momentum, all kinetic. And then this one moves off negative m1v final plus m2v final this way. Now notice, big notice here, that these are both going to be positive with energy because energy is speed. So what I didn't note here, and this is, again, the symbols become like really, really tough here. But typically, when you're talking about velocity, it's like a sharp V like this, okay? And V is volume later too. And when we're talking about speed, we're talking about this V, but it's got like this, it looks like it's blowing in the wind like this. You see that V? So these should really have this V going like this to denote the fact that the sign doesn't really matter on this. It's always positive. It's energy. It's positive. Now you're going to learn later on when we get to potential energy of a system, negative GMM over R, that you can't have negative energy. But for now, it's positive, okay? We'll deal with that when we get to that. So next case, mass 1 equals mass 2. What do you think is going to happen here? Well, this guy's moving. This is just like you're playing pool, okay? Equal masses. This one comes to strike mass 2. This one is 0. Strikes mass 2, mass 1 stops. You see that? So this one's moving, strikes this one, now this one picks up the speed. Okay, So it's like an equal transfer. So it's like Newton's cradle when you've seen those beads that go tick, 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 tick back and forth. That's what this is. Okay, so qualitatively, again, I want you to understand just what's going on here. Well, if it's smaller, it hits it and it bounces back. If it's equal, it hits it, stops, and this one's moving. Now notice the one common variable here is mass 2 always moves to the right. That's the one common variable here. Now what if mass 1 is greater than mass 2? This is another scenario here. Well, mass 1 is greater than mass 2 here. So here's mass 1 moving to mass 2. So what's going to happen is it's going to strike mass 2, and they're both going to move off to the right. So qualitatively, I want you to understand that again, mass 2 has no momentum, no energy. Mass 1 carries the whole thing for the system. And then they strike, and now they both go off. So these are both positive because the velocities have to pick up the signs, but again, the energies don't ever pick up the signs, right? So that's always positive. Now, special equations. These equations come from this situation where mass 2 is at rest, and you want to find the final speed of 1 and the final speed of 2. If you plug these situations in, you will find the sign of this to be true. Like, in other words, like that, what's the final speed of mass 1? Well, if mass 1 is greater than mass 2, then this has to be positive. And then this one is always positive. So mass 2 is always going off to the right. If mass 1 equals mass 2, then V final 1 is 0. So these describe what I just showed you qualitatively, but I would like for you to memorize these equations because they come in handy. And as long as you set up your equation, your momentum, your energy, you can go to these. These are nice shortcut equations for a one-dimensional situation where mass 1 is moving and mass 2 is at rest. So this is good stuff here. I definitely would not put this down and commit that to memory because it's going to help you out a lot. And this also applies to a situation like I've seen a problem before like this, like there's like a bead hanging like this, and then there's like it's like a kind of like a Newton's cradle, but Newton's cradle would be like that this is the same mass and this hits this one and then this one stops and this one keeps going. But I've seen situations before where you have this and let's say one is like this, but this one is a smaller mass. So it comes and it hits it, and what happens is it mimics this one-dimensional situation. So when it comes down and hits, when it comes down and actually hits, what's going to happen is it's going to mimic that situation where mass 1 is less than mass 2, so this one's going to rebound back and this one's going to go this way. So these come into play in other situations too. So qualitatively, again, you need to understand how these behave. Okay, so let's talk now about a 1D elastic collisions, but let's just say that mass 1 and mass 2 are both moving. So the situations we just saw, mass 1 was moving and mass 2 was at rest initially. Remember that? So in that situation, there was no V2 initial. So those are the equations that I just gave you a second ago. That's what these are. But what if mass 2 was moving into it? Well, in essence, what you would get is you would get this second term. So V1 final would be M1 minus M2 over M1 plus M2 V1 initial plus 2 times M2 over M1 plus M2 times V2 initial. V2 final is 2 times M1 V1 initial over M1 plus M2 plus M2 minus M1 plus M2 V2 initial. Now notice, one thing about these equations too, they will give you the proper signs. So it's a strange thing. You're combining speed from the kinetic energy with velocity from the momentum, but you will end up with the correct sign. So if this is a negative answer, it's going to the left. If you define your positives in this direction, a negative is going to the left. This is a positive going to the right. Same thing with this. So that's important with that. So should you memorize it? Why not? Why not? Because you definitely don't want to derive this. Now, most of the time they're going to give you enough information, you know, initial momentums, final speeds. They'll give you enough clues. You may not even need to use this, but in case you do, that's what it would be. Now, two-dimensional elastic collisions. So let's take this situation here. You have two different masses. You have mass 1 and mass 2, okay? And they're moving along a line here, and mass 1 is moving initially here, okay? So this mass is going to mass 1 is going to strike mass 2, and they're going to go off in different directions. Okay, so you're going to have V final 2, and you're going to have V final 1, and you're going to have theta 2 and theta 1, like this. Okay, so notice in the beginning, where is your momentum? So if I put my system here, I'll put it around both of them actually. So I'm dealing with all internal forces. There's no impulse. There's nothing coming from the outside. They're just coming and it's going to strike. So my initial momentum is just going to be along the x, only along the x. So if they move in different directions along the y-axis, so let's just do these in different colors here. Let's do the x with the blue here, and they're not necessarily the same. And we'll do the y here. Ooh, change the size of the pen there. Okay, so let's do the blue here. The blue here is going to be the x here, and let's make the green the y here. Now, the momentums of the y's should be equal in magnitude. Why should they be equal and opposite? Because there was no initial y momentum here. They have to cancel out. So this momentum 2 in the y has to equal momentum 1 in the y because there's no net momentum in the y. And then the x here is going to split up. So it splits up into components just like forces. So you treat it very much the same way. So again, some of the forces, some of the momentum in the x equals net momentum in the x. And so initially, the total sum of the momentum was just m1 v initial 1 here. And then it moved off into cosine. So m2 v2 final times cosine theta 2. So again, that was the x component there, plus m1 v1 final times cosine theta 1. So both of these added up. So that's one equation. So I have to get another equation here. So I have theta 1, I have theta 2, depending upon what they gave you. Depending on how many unknowns you have, you may need to keep going with these equations. This is a symbolic example, but again, it depends what you're given. And now if you look at the y here, the y, we started with 0 momentum in the y because everything was going along the x. Everything was going this way. So m2 v2 final sine theta 1, which was going up in this way, minus m1 v1 final sine theta 1 here going this way, and they have to be equal and opposite. So again, depending upon what you're looking for and what unknowns you're given, I mean, they might give you v2 final or whatever, just they might give you both v1 and v2 final, and then you really don't have to do so much work. But if they didn't, then you would have to throw an energy into here. So you would say m1 1/2 m1 v initial 1 squared. That was the mass of this one traveling like this first. That's the total kinetic energy of the system because this one's not moving. Equals 1/2 m v final 1 squared plus 1/2 m v final 2 squared. And again, now here's another thing about energy. So this is two major differences here that we got to keep in mind. Okay. Number one, we said that energy here, which I'll draw with my little V's that are blowing in the wind here, okay? First of all, there's no negatives or positives, okay? That's the main thing here. And we're not dealing with components, okay? So that's two major differences here. Remember, the momentum picks up the positive and the negative signs because we're dealing with V, which is velocity here. But these are speeds, so there's no positive or negative. It's just all positives, okay? It's all positive. Positive energy on this side equals the total energy on this side. So E initial equals E final in terms of kinetic energy initial equals kinetic energy final in this case. That's the first thing. The second thing to look at is we're not dealing with components with energy, okay? It's just the total kinetic energy here equals, so we're talking about total kinetic energy over here, and we're talking about the magnitudes. So we're saying V here, and we're saying V cosine theta for the momentum and V sine theta for the momentum. that this is important to get the components because we're talking about x's and y's. Energy doesn't care about that. It just cares about this, the magnitude, which would be the speed. Magnitude would be the speed. So again, two major differences to be careful for.